Hello, my name is Maxim, and today partner and I will present you automotive safety assessment for a line-centric system. And it's a part of automotive system safety and cybersecurity. We will observe a lot, but first of all, we will start from customer point of view. Yeah, just because of it's understand how it works. LCAS, yeah, just helps the driver keep a vehicle centered in a detected lane, and designed to operate at 45 mil per hour till 90 mil per hour. And LCAS uses small corrective steering wheel inputs, but you are always retain full command of the vehicles. And LCAS is not hands-free system, and the driver must keep a hands on a steering wheel all the time. And it's vital to understand LCAS is not an assist tool and will not work in all traffic situations and under all circumstances, weather and road conditions. And from customer point of view, yeah, just we will look at functions and limitations. Yeah. And functions, it provides the corrective steering for lane keeping, warns unintended lane departure, increase safety by keeping the vehicles within the line, and warns driver before deactivation. And the limitations, yeah, just it's also exist. Yeah, just for example, lane corrective limits, or weather and visibility dependency, or requires minimum lane widths. But what we did, yeah, just we opened official Mercedes-Benz site and find, yeah, this following situation where LCAS is not functioned well or not functioned at all, and split it to three categories. And first of all, it's a sensor set, yeah, just because of pure visibility, because of rain, snow, fog, or heavy spray, or sun reflection, for example, glare, or door to windscreen, yeah, or damage or covered. Yeah, just don't work because of sensor set is cameras. Computer vision algorithms, yeah, when you don't have lane markings, yeah, just or your lane markings worn out, unclear, or covered to something, yeah, just or distance to the vehicles in front it's too short and you see only bumper to bumper. Yeah, just in ablation speed, it's when the situation's changed so fast and you don't have time to think. Yeah, this, for example, you cross one another or match lines. And just because of sensor set and computer vision, it's 90% of all the problems we will observe very fast. Yeah, just these algorithms in 4 pictures. In the right side. First of all, it's a screenshot. Yeah, just from the video. Yeah. Second one, it's a gray image. Yeah, just absolutely the same. And third one, it's a kind of edge filter. When you see not pictures, yeah, just but only edges of objects. Yeah, just and the last one when we cut everything out. Yeah, just except of region of interest of our algorithms. And other slides will be presented by Parta. Thanks.
Thank you, Maxim. In the literature study, we found camera-based systems are the most common technology used for the lane detection, but it has its own drawback. They are dependent on the visibility. Laser, infrared cameras are used to complement and overcome this drawback. The state of lane keeping systems are based on the machine learning and deep learning technologies. With the increasing complexity, ISO 26262 process and practices are not sufficient to cover all possible hazards. Standard which focuses more on artificial intelligence and deep learning techniques is required. In this slide, we look into different standards used for the assessment. ISO 26262 is the industrial standard for functional safety of road vehicles. It provides a process for safety in hardware as well as in software. It focuses both on the random failures as well as the systematic failures. However, it does not guide well on how to get the extensive failure list on its own. From the literature study, we identify that to overcome this, other systematic methods such as fault tree analysis, system theoretic process analysis, fault mode and effect analysis can be used to determine the list of failures. STPA is fairly new and gaining traction. Fault tree analysis is very intensive. For this exercise, we choose the old proven FMEA as a method of choice. It contains 5 steps: structural analysis, functional analysis, failure analysis, action analysis, and optimization. This slide shows the block diagram of the system, which is developed for the system description. Information from the driver input, vehicle parameters, environment parameters are measured by sensors. Different specialized ECUs perform the lane assist calculations and controls the actuators in the vehicle. We also have shown the structural decomposition of the lane assist function. This helps us to understand the different components and their system boundaries. Based on the level of detail required, we can further decompose on the individual components from the system level. The next slide shows the functional architecture of the lane keep assist system and its function net. The detailed function net will help us in understanding the control flow and the functional significance of different components. Here, the lead path performs the analysis on the lane ahead and predicts the motion required for the vehicle. The current path monitors the lane lines in the close quarters and ensures that the vehicle is in the center of the lane. After the functional analysis, failure analysis is done. And from that, now we have the list of failures from the FMEA. The major faults are crossing the lane, traveling on the lane, abrupt deactivation, failure to notify the deactivation, failure to deactivate on user intervention, improper speed adjustment, especially in case of ACC. These are life-threatening hazards. We also have few minor ones. The minor ones are annoying to the driver, but not life-threatening. So some of them are not in the center, the vehicle not traveling in the center of the lane, but within the lane, low frequency oscillations inside the lane, and failure to activate. According to American Automotive Association research, nearly 73% of the errors on the public roads are life-threatening. In the next step, the failure list from FMEA is converted into ISO 26262 recommended terminology and added to the hazard and risk assessment analysis template. Combination of 3 factors determines the ASIL ratings. The severity tells how bad the safety consequences in the hazard takes place. The exposure tells the probability of occurrence for the given hazard. And the controllability is the measure of how good the driver can control the hazard scenario. ASIL classification is done as per the ISO table provided here. We have used this table to calculate the failure which we have identified from the FMEA. As you can see, the hazard with this highest severity rating have S3 for the severity, the exposure rating with E4, and the most difficult controllability C3, giving us the highest possible ASIL rating, ASIL D. There are various methods by which the experts can come up with the S, E, and C values, but we have used the information we gained from the FMEA. The goal of ISO 26262 is to prevent harm. ASIL ratings help us to achieve the goal-based approach to develop a safety system. With the ASIL rating, managing and tracking the safety requirements becomes easier, and it helps in prioritizing and organizing our safety goals. For the next slide on control and corrective actions, I would like to hand over to Maxim.
It's Maxim again, and we will observe top 3 risk of accidents. And case number 1, a lane correcting application does not bring vehicles back into the original line. And case number 2, LCAS does not detect traffic conditions or road users. And case number 3, in such cases, LCAS could give us unnecessary warning or not give a warning at all. In a very rare cases, the system may disengage, for example, after over solid lane markings. And these 2 pictures, it's a real challenge for the LCAS algorithms. Pictures below, for example, it's a real picture from my native town, and pictures upper, just with a tunnel, it's a real change because of the cameras and their structure. About conclusions and recommendations. Conclusion number 1. LCAS are overly active when the driver is focused, but too passive when he is distracted. And if we combine driver monitoring system with any ADAS, just ADAS probably will be a secondary security system and interferes only when it's really necessary. For example, when the driver is exhausted or disorientated or have some medical issues. And conclusion number 2, drivers get too much relied on this type of the systems, and maintenance and repairs of any ADAS system is highly costed. And of course, we know each country has obligatory technical inspections for lights, for brakes, for windshields, but ADAS, it's not in the list. And if the drivers get too much relied on the system without maintenance, and it could lead to the extreme unsafety scenarios. So for today, it's all. Thank you for your attention, and bye bye.